Encapsula Nanosciences presents Liposome Basics Part 2. Here we describe the basic methods for preparing and sizing liposomes. The simplest method for preparing liposomes is hydration of dry lipid. The lipid is dissolved in organic solvent along with any lipid-soluble compounds to be incorporated into the liposomes. The solvent is commonly removed by rotary evaporation, resulting in a thin film of dry lipid. Some solvents can be removed by lyophilization, resulting in a dried lipid cake. An aqueous solution containing water-soluble compounds to be encapsulated is then added to the lipid film or cake to hydrate the lipid and form the liposomes. The aqueous suspension must be heated above the phase transition of the lipids in order for the liposomes to form. The resulting multilamellar liposomes consist of many concentric lipid bilayers. While all or most of a lipid-soluble compound will be incorporated into the bilayers of these liposomes, the amount of water-soluble compound entrapped is usually very low because these MLVs have a small captured volume. Very little aqueous solute penetrates the onion-like layers of hydrated bilayer lipid. The captured volume of these MLVs can be increased by freezing and thawing the liposomes several times. Repeated freezing and thawing ruptures and reforms the MLVs, resulting in an increased number of liposomes with fewer layers of lipid and more aqueous space inside each liposome. Thus, the freeze-thawed liposomes encapsulate more aqueous solute and often have a multivesicular morphology. The aqueous solute is now uniformly distributed inside each liposome. The thin film method is limited to laboratory scale, while the reversed phase evaporation method can be used to produce milliliters up to thousands of liters of liposomes. Lipid is dissolved in organic solvent along with any lipid-soluble components. The aqueous compound is added to the lipid solution. This biphasic mixture is then emulsified by some form of high shear mixing. The organic solvent is evaporated from this emulsion, forcing the lipid into the aqueous phase, where it organizes into bilayers and forms liposomes. Additional aqueous phase is added in order to complete the liposome preparation. Again, the temperature of the aqueous phase must be above the phase transition temperature of the lipids in order for liposomes to form. Unlike MLVs produced from a thin film, liposomes produced by reversed phase evaporation usually have one up to a few bilayers per liposome. Like freeze-thawed liposomes, these liposomes can be multivesicular and have uniform aqueous solute distribution. Liposome characteristics can be optimized for a particular formulation by systematically varying the process parameters. Many variations of these methods are described in the scientific literature. Liposomes produced by these methods have a broad size distribution. The only method which can produce a definable unimodal distribution of liposomes in the 100 nanometer range is high-pressure extrusion through membrane-type filters of a fixed pore size. The stainless steel device which supports the filters used for extrusion withstands internal pressures in excess of 1000 psi. Extrusion cannot be accomplished with standard liquid filtration devices. Larger extruders are pressurized by nitrogen, while extruders handling volumes less than 1 milliliter utilize gas-tight syringes to generate pressure manually. Extrusion must be carried out above the phase transition of the lipids in the liposomes. In order to achieve a narrow size distribution, the liposomes must be passed through the filters 10 times or more. The liposome suspension becomes more translucent during extrusion, indicating that the liposomes are becoming smaller. The lower size limit of a liposome is 30 to 60 nanometers, depending on the type of lipid used. High shear methods are used to reduce multilamellar liposomes to unilamellar liposomes at their lowest size limit. Most water-soluble compounds must be present at the time the liposomes form to be encapsulated. Some ionizable compounds can cross the membrane in their neutral form and be converted to an insoluble salt form inside the liposome. This remote loading technique allows drugs to be loaded into liposomes after the liposomes are formed, but is not widely applicable. Some ionizable compounds can also be loaded into pre-made liposomes with a pH gradient. In this example, the neutral form, but not the charged form of a compound can cross the membrane into the liposome, but can't escape due to the high concentration of protons inside the liposome. Lipids organize into bilayers due to the presence of water. When the water is removed by lyophilization, the bilayer loses its structural integrity. After rehydration, the liposomes have a different size distribution and have leaked their entrapped contents. Some aqueous solutes, such as sucrose, can replace water at the lipid head group, thus maintaining the bilayer structure when water is removed. In this case, the liposome can be lyophilized, then rehydrated while retaining its original size and entrapped contents. Membrane proteins can be studied in their native state by incorporating them into liposomes. The protein and lipid are co-dissolved in a detergent solution. When the detergent is slowly removed by dialysis, the protein incorporates into the newly formed lipid bilayer. For more information about liposomes, go to our website at www.incapsula.com.